In this lesson, we're going to talk about the periodic table and what makes it unique. The periodic table was, in its modern form, was conceived in 1869 by the Russian chemist Dmitry Mendeleev. This is the basic outline of it. Now, his periodic table didn't look like this per se. He instead was the first one to realize that there's a repeating pattern and that some elements hadn't been discovered yet. That was the really key part to establishing the repeating pattern or the periodicity of the periodic table. If you glance at the modern periodic table, the most up-to-date version, you'll see 118 elements. They've named them all now. For a while in recent years, they had named them with like Latin for the name for the number, the atomic number. But now they have finally gone ahead and named every single element and given every element either a one or a two-letter chemical symbol. Here's some basics. It'll be helpful to have a periodic table out as we go through this. When we say the word group in chemistry, it means something very specific. It means a vertical column on the periodic table. Okay. Yes, groups is used colloquially to mean any grouping, any putting together of objects. Of course, we still use it in that way. But when referring to the periodic table and we use the word group, we mean vertical column and the elements in that column. When we say period, we mean a horizontal row on the periodic table. So groups are vertical columns. In groups, you have elements that react similarly. In horizontal rows or periods, you have elements that have outer electrons in the same principal energy level. Now, that concept of same principal energy level, we're not going to get to until Unit 4, so it'll take a little while to understand what that means, but it basically means their electron arrangements are similar. But the far more important distinction is the groups. So elements within a vertical column all react the same way, and that's far more important in terms of being related to another element than it is to have electrons in the same principal energy level. Another really, really important distinction on the periodic table is the dividing line between nonmetals and metals. So if you find your periodic table and go to group 13, you'll see that there's boron at the top with a B, and you'll see right below that aluminum. So between boron and aluminum is a horizontal line that cuts, dividing a full-fledged metal in the case of aluminum and a full-fledged nonmetal in the case of boron. But then if you go straight down and then to the right, down and to the right, down and to the right, and down, and then actually to the right and down, because now we have these bottom elements fleshed out, you would have a dividing line that has these blue elements. See how they're color-coded blue? Those are called metalloids. These are elements that have properties between those of metals and nonmetals. So if you're not bordering this downright line, which they call either a zigzag line or a stair-step line, then if you're well off to the right, those are the nonmetals. If you're well off to the left of that line, it's metals. And I would point out there's a goofy element, hydrogen, that kind of defies categorization. It is a nonmetal, fully nonmetal, listed on the left side of the periodic table. Generally speaking, the nonmetals are different from, or the metals are different from nonmetals in that metals conduct heat and electricity. They can be hammered into sheets. That's a property called malleability. They can be drawn into wires. That's called ductility. And they are, when they're on their own and not mixed in with lots of other impurities, they are shiny. So like if you take a brand new copper penny, copper's a metal, it's shiny. But if you have a bunch of gunk on the penny, it's kind of old, scuffed up. It's going to be less lustrous than a brand new penny. So provided that it's clean, you have a shiny material in the case of metals. The nonmetals would have the opposite. So nonmetals do not conduct heat and electricity. They're not malleable, they're not ductile, they're not lustrous. In fact, if you were to take a hammer to a nonmetal, well, let's take a look at what would that look like? If you were to take, let's say, this is a sinker, which is something you put on a fishing line to make the lure go down. If you were to take a hammer to that and smash it, it would just smush a little bit. It would not break. It would just kind of move out of the way of the hammer. And the reason for that, deep down, has to do with electron ownership. Electrons within metals are loosely held. There's not a heavy claim of the electrons for one atom to another. They're just kind of very loosely held among all of the nuclei in a grouping. And so when you smash it with a hammer, the electrons can move around and the material doesn't snap. Contrast that with if we take an ionic compound, for example, where the metals and the electrons are held very tightly by the atom. If you were to hammer an ionic compound, it might momentarily cause an alignment of similar charges together. So positive next to positive, negative next to negative, and that would, of course, because similar charges repel each other, would cause the material to break. So when you hammer a non-metal or an ionic compound, which consists of the combination of a metal and a non-metal, it's going to break when you hammer it. We'll have a chance to test this in lab. It's kind of a cool thing. Other important groupings as we take our tour of the periodic table. Remember, the vertical columns are the groups. A few of the groups have special names. In fact, if you look this up in a textbook, they all have special names, but the most important of those are the ones that are shown here. The very first column, column 1, consists of the alkali metals. Now, hydrogen is a non-metal, so we have to exclude hydrogen from that category. But all of the elements below hydrogen in column 1 are alkali metals, and they're extremely reactive. Those are some of the most reactive substances out there. Column 2, we call them alkaline earth metals. The middle block of elements are called transition metals. And the reason for that has to do with how charge is held. We'll get to charge category, we'll get to charge categories next unit. But every grouping in the periodic table, because of the electrons that are owned by it, has a particular charge that is associated with that column, and all of the elements within that column bear that charge as well. In the case of transition metals, they have variable or transitional charges. So that's why they call them transition. They can have 2 or more, maybe even 3 or 4 different charges residing on that element, but everything else has a definite single charge that it carries all the time. Column 13, you could call it the boron family. There is a technical name for it that I don't even know off the top of my head. The carbon family, because carbon's at the top of the next column, the nitrogen family, the oxygen family. Those are less important naming-wise. But when you get to group 17, that's important. When we say halogens, we're talking about the elements below and including fluorine. So fluorine, chlorine, bromine, iodine, astatine, and tennessine are all halogens, and they are of the more reactive types of elements as well. In the very right column of the periodic table, we have noble gases. Noble gases do not react, and again, that has to do with their electron ownership. They have full shells of electrons, and therefore they don't have much incentive to react. They're happy being alone, and you might think of it as being noble and aloof and not needing to interact with other elements. Okay, take a look at this grouping down at the bottom called intertransition metals. If we had, well, if the elements on the periodic table fit nicely onto a standard sheet of paper, we would expand this periodic table and make it twice as wide as it is and about half as tall as it is. But since our standard sheets of paper are 8.5 by 11, it's just a lot easier to say, okay, look, there are these elements down at the bottom called intertransition metals. Turns out we don't end up using them all that often in our course or general chemistry courses. But we basically insert that two rows right here next to lanthanide and actinium, lanthanum and actinium. They call them lanthanoids and actinoids because you could literally expand out this periodic table and push it wider. Let's talk a little bit about noble gases. I mentioned that they're non-reactive. These are the only elements that are found uncombined in nature. So if I were to draw a particle diagram of one of the noble gases, let's say a sample of argon, which is one of those, I would see individual atoms of argon, Ar is its symbol, not touching each other and not touching anything else. They're just plain atoms, not doing anything else. The other thing that's important to note is some of the elements, when they do bond, they're going to bond with each other. And they form what are called diatomic molecules, meaning two atoms of the same type. Like here's nitrogen, chemical symbol N, bonded to another atom of nitrogen, chemical symbol N. That's how the clusters of nitrogen atoms exist in the world. Here's another one, oxygen, two atoms of oxygen bonded together. That has profound ramifications for when we study chemical reactions and we go to balance equations. We need to remember that certain elements like nitrogen and oxygen form clusters of two atom molecules called diatomics. The 7 elements that form diatomics, and yes, you'll have to memorize these, are hydrogen, which forms the molecule H2, nitrogen, N2, oxygen, O2, fluorine, F2, chlorine, Cl2, bromine, Br2, and iodine, I2. Now you can arrange these symbols into a pronounceable order, and I'll show you, I'll teach you the mnemonic. You could say Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine, Hofbrinkel. I've also heard Hoberfinkel, if you prefer. That would just flip the bromine and the chlorine. Hoberfinkel, or switches a few of the elements. In any case, you do need to be able to identify these 7 and recognize it when you see them. Okay, last bit. On the periodic table, the goofy number that's not a whole number in each of the boxes is the average atomic mass. And the way we get that, the average atomic mass, is we consider what isotopes exist and how abundant they are in nature. So take carbon. Carbon, there's actually more forms or isotopes of carbon than what is shown here, but use this as a nice example. Let's say that we have 2 forms or isotopes of carbon, carbon with a mass number of 12, which we call carbon-12, and carbon with a mass number of 13, carbon-13. Recall that a proton, the number of protons that an atom has, is what defines it. So if we were to count up the number of blue spheres in each of these diagrams, we should count 6 because that's the atomic number for carbon. So 1, 2, 3, 4, 5, and 6. If it's carbon with a mass number of 12, we should have 6 neutrons as well, because the mass number minus the atomic number, since mass number is sum of protons and neutrons, and atomic number is just the plain protons, if you subtract it, you should get the number of neutrons. Let's count the number of neutrons in the top atom here. 1, 2, 3, 4, 5, 6. So carbon with a mass number of 12 has 6 protons and 6 neutrons in its nucleus. Let's look at the other one, carbon-13 below. Count the blue spheres first. 1, 2, 3, 4, 5, 6. 6 protons. And let's count the neutrons. We would expect to see 7, mass number of 13, minus an atomic number of 6. We have 1, 2, 3, 4, 5, 6, 7. So 6 protons and 7 neutrons in carbon-13. Now here's where the abundance comes in. It turns out in a collection of carbon atoms found in nature, 99% of them will be carbon with a mass number of 12, and just 1% will be carbon with a mass number of 13. To account for that percent abundance, what we're going to do is take the percentage and state it as a decimal. If you remember this from math class, you're going to divide by 100 and move the decimal 2 places to the left. So 99% written as a decimal is 0.99. 1% written as a decimal is 0.01. We take those percentages stated as decimals and times it by the mass number. So 12 times a decimal of 0.99 plus, and then use parentheses, 13 for the mass number of the other isotope times its percent abundance stated as a decimal, 0.01, allows us to, if you crunch the numbers here, 12 times 0.99 is 11.88, and 13 times 0.01 is 0.13. And we simply add the two numbers together and get an atomic weight of 12.01. In other words, that's an average of the atomic mass or atomic weight of the isotopes of carbon that exist, accounting for their percent abundances. We call that calculation, shown here, the weighted average. Now, I invite you to look on your periodic table and find carbon. You'll see atomic number 6. You'll see the symbol C. You might see the word carbon written out. And the decimal written is 12.011, which is almost 12.01. And you might say, yeah, how come it's not 12.011 exactly? Well, we actually rounded these percentages. It's not exactly 99%. It's something like 99.023567%. And rather than 1% for carbon-13, it's like 1.1392456%. I'm making up numbers there. The point is, we had nice whole percentages here, and that's not necessarily the case. Thank you for listening. Good luck on the homework.